Okay, so this is the answer key tutoring video for your unit quiz. And it's not the second one, but this is your pretest quiz that we took in class. So here we go. So the first one here, we need to find your balance, total, and net ionic equations from an aqueous solution of strontium nitrate and sodium sulfate. All right, so a few things about each one of these steps. First, we need to get our reaction down. So strontium nitrate. Now strontium has a +2 charge, so I need to bring that 2 down to there. And it already says that it's aqueous. Aqueous. That is added to sodium sulfate. Now sulfate has a -2 charge, so that's why there's a 2 there. And that will produce, and that's going to be aqueous as well. And that's going to produce, let's see here, what do we have first? Strontium sulfate. Both of those +2, -2, so those charges cancel out. And that is going to form a solid. So I should have seen the solid sign here. And that's going to be added to, let's see here, NaNO3, and that's going to be aqueous. And then there's going to be a 2 here for it to be balanced. So that's all we need to see. All of this, reactants, products, solubility signs, and then a correctly balanced equation to get 3 points for that first question. All right. The second part, total ionic. So what I'm going to do is I'm going to copy everything straight down, SR, and then anything that's aqueous, I'm going to split apart. So SR, and I'm going to add the charge above it. And this 2 tells me there's going to be 2 NO3. So I'm going to put 2 NO3s. Each one has a -1 charge. And I'm going to add that 2 here. Once again, I have 2 NAs. That's split with a +1. Sulfates with a -2. That's going to give us, once again, because this is a solid, we do not split this apart and we do not put any charges above it. We're going to just bring it straight down and leave it alone. And then put the solubility sign. And then, so this 2 goes with both of those. So I technically have 2 NAs, each with a +1. And then I also have 2 NO3s, each with a -1. Okay? So for this one, I would need to see your dissociation lines for all of your aqueous solutions. Leave your solid alone. I would need to see the charges above each one of these because they got broken to their ions. Once again, leave this alone because this did not get broken into its ions. Okay? Come down here to your net ionic. So the last part of total ionic, we should be able to cross out all your spectator ions, which is going to be, I have 1 NA, or I have 2 NAs here, 2 NAs here, I have 2 NO3s here, 2 NO3s here. So there's all your spectator ions, and I bring everything down that's left over. So strontium +2 is added to sulfate -2, and that gives us strontium sulfate over here in the solid form. So I would need to see the charge, strontium sulfate together with your solubility sign here, and then each one of these was worth 3 points as well. Okay? Coming down here to the bottom. What is the molarity of the solution resulting when 200 milliliters is added to 10 milliliters at 6 molar concentration? So if I look at my dilution formula, M1V1 equals M2V2. All right, I'm looking for my M1. This 200 is in milliliters. I need to change that to liters. So 1, 2, 3, this should be 0.2 equals, once again, milliliters needs to be changed to liters. So 0.01, right? 1, 2, 3. And this is going to be my molarity of 6. So when I do that and put this into the calculator the correct way, I should get 0.3 as my answer. However, when I look at all of my givens, they all have 3 sig figs. So that means I need to have 3 sig figs here. And this is going to be, what is the molarity? molarity, and that's just going to be a large M. There is my answer. Okay. On number 5, how many milliliters, so that's going to be a big step here, results when 5.45 grams of sodium chloride makes 1.5 milliliters. So I have two variables here, which means I need to use my molarity equation, which is M equals moles divided by volume. Now that volume needs to be in liters, just like it was up here. And I need to, but my answers needs to be turned into milliliters. We'll get back to that in a second. So the first thing is they give me my M. I need to find the V, which means this 5.4 needs to be, because this is moles, this 5.4 needs to be turned into moles. So I take 5.4 grams sodium chloride, and I get out of grams of sodium chloride and into a mole by the molar mass, which should go right here. The molar mass, 58.44. So when I divide that by that, I should get 0.093 to be plugged in right there. Okay? So when I divide this, so to get this by, or start to get V by itself, multiply both sides by V, and then divide this side by 1.5, which means I'm taking 0.93 and dividing it by 0.093 divided by 1.5, I should get, where are we? 0.062. Now the thing is, this answer is in liters. I don't want it to be in liters. I need it to be in milliliters. So I just move the decimal 1, 2, 3 spots back to the right, and now I get 62 milliliters as my answer. Check sig figs. Well, I have 3 here, I have 2 here, so it means I need to use the lower of the 2 amounts, which is 2. I have 2 sig figs there. There is my answer. Okay. Number 6, how many grams? So there's a little thing that we need to come back to of calcium hydroxide can prepare 1.5 liters of a 2 molar solution. So set up my equation again over volume, right? So I have 1.5 liters. That's a good thing because I don't need to convert anything. And they give me a molarity of 2.0, which means I need to find my moles. So when I take multiply by 1.5, do the inverse operation to get rid of this, and then multiply this side by 1.5, that should leave me with the moles. So 1.5 times 2 gives me 3.0. Okay. However, that's in moles. I need a mass. So this is currently moles of calcium hydroxide. All right, because calcium has a +2 charge, that transfers down over here. All right, so what do I need to do to get out of moles? All right, 1 mole of calcium hydroxide is equal to its molar mass of calcium hydroxide. Well, the molar mass of calcium hydroxide is, let's calculate that, so 15.999 times 2, add that to 1.008 times 2, and then add that to, actually, let's start over, 15.99 times 2, add that to 1.008 times 2, and then add it to calcium's, which is 40.078. I should get 74.092, and then I multiply that by 3, and I should get, as my calculated answer, 222.276 grams calcium hydroxide. Now the problem with that is I have 2 sig figs, which means down here I should be using 2 sig figs. So 1, 2, that means there's my cutoff. I need to use this to round that or keep it the same. So when I do that using sig figs, 220 grams calcium hydroxide is my answer. Okay? On the back side, all right, which solution is more? So I have this up here, 25 grams of sucrose is dissolved into 500 milliliters of water. That's my first solution. All right. So then she adds 250 more milliliters of water to solution 2. So which solution is more concentrated? So which one has a higher concentration of this sucrose? So which one can we have will be more of this in it? Well, if I've added more water to solution 2, I just diluted it some. All right. So that means solution 1 should be your most concentrated of the two. Which solution contains the greater number of moles? Well, if I start with this amount and I just add water to it, I didn't take any of this away, I didn't add more of it to it, it's become less concentrated, but I didn't add any or more grams of sucrose, so my moles doesn't change either. I still have the same amount in each one. Which solution would have the lower molarity? Well, molarity is just another word for concentration. Okay, so which solution would have the lower molarity? So if this was solution 1, this one's got to be solution 2 because it's become less concentrated with adding more water. How would Susie increase the molarity of solution 2? All right, so if we want to increase the concentration of the sucrose in solution 2, well, by adding more, we would just dilute it more. If you add both equal amounts, then it would keep the concentration the same, so we would have to add more of your solute to get there, okay? Using this graph for the next couple here, how many grams of SO2 are needed to saturate 100 milliliters? Now, over here it says 100 grams. Well, 1 milliliter equals 1 gram. All right, that's a good thing to remember. So I'm looking at SO2, which is right here, are needed to saturate 100 milliliters of water, which we already have, at 40 degrees Celsius. So 40 degrees, it gets to be about right here. So your answer is approximately right there, 5 grams. All right. What is one graph substance that behaves as a gas? So a gas should be trending down like so. A solid or liquid will trend up like that. So you could have had SO2, because that trends down. You could have had NH3, because it also trends down. And you also have HCl. Now, HCl is not necessarily a gas, but it does behave as a gas, like you can see here, because it's trending down. All right. So the next one, 20 degrees Celsius, 5 grams of KClO3. KClO3 is this line here. Is dissolved in 100 grams of water. Is this solution? So I have 20 grams, 5. So right there is where I'm looking, and I'm looking at the KCl line. Well, this dot falls below the KClO line, so that means it's going to be unsaturated. If it fell on the line, it would be saturated. If it fell above the line, it would be supersaturated. But in this case, it's unsaturated. Okay. The next one, using 200 grams of water. Now that's a key thing we're going to come back to. How many grams of KNO3, which is right here, KNO3, would be dissolved at 60 degrees Celsius. So what we're going to say is we're going to think of it as 100 grams right now. So with 100 grams of water, which is what the chart shows, KNO3 can dissolve, well, here's 60, can dissolve about 105. So at 100 degrees, it can give me about 105 grams of KNO3. So the problem is I'm at 200 grams of water. So to get from 100 to 200, I've just doubled the amount of water, right? So that means I should double the amount of what can be dissolved at 100. Our temperature does not change, so when I do that, approximately 210 grams of KNO3 can be dissolved in 200 grams of water. Okay. Number 15, if 100 mils of 55 degrees saturated solution of NaNO3, which is, so 100 mils of NaNO3, this is this line here, 55 degrees, So we're looking at about 120. We start at 120 not degrees grams of solution, but now it's cooled to 35 degrees. So 35 is about right here, and that's about 100. So it's gone from, it can only dissolve 100 grams. So at 55 we can dissolve that amount. At 35 we can dissolve that amount. Well, if we start with that amount, how much will fall out of solution? How much will no longer be able to dissolve? So 120 minus 100 should give you 20 grams. Okay. Next page is this one. Circle all the compounds that are soluble in water from the list. So what we're looking here is for polarity. Okay, so what we should ask ourselves is ionic versus covalent. Well, I see covalent here. I see covalent here. I see covalent here. The rest are ionic. So the rest of these we should be able to check our chart, and when we look at our chart the right way, we see that actually this is ionic. This is not, because NH4 is a positive charge, so this is not covalent. Your only covalent ones are these two. Okay, so we should see that. What do we have? From our chart, this will be aqueous in water. This will be aqueous in water, and this will be aqueous in water. Okay. Now the rest of these we need to look at. And we see that N2 is actually this when we draw it, which means it's non-polar. Because water is polar, this will not dissolve in water, so we do not circle that. NH3, this is a polar molecule, and water is polar, so like dissolves like. That should be circled as well. So those are the four that should be circled. Number 17 was not graded, so don't worry too much about 17. 18, the rate of solubility. So this is how fast can we get things into solution. So the first thing is temperature. Temperature increases, we can get it in faster. So raise the temperature. The second thing is we can crush it or increase the surface area. Okay, we can crush it, or we can stir it or agitate. Okay, heat it, crush it, stir it. Those are the three things that you saw in your PowerPoint. They should have seen that affect the rate. That's the big key word there here. So in order to dissolve more oxygen, which is a gas, to remain dissolved in a lake, the temperature must be. So with gases, it's a little bit different, because as we decrease temperature, we can actually get more gas into a solution. So the correct answer here is cold. The colder the water, the more we can get, the more oxygen that can be put into it. Number 20, the diagram below represents the dissociation of a binary ionic compound, which best explains the arrangement of the ions in the water. So what happens here is we have our potassium bromide, our ionic compound, put into water, which breaks apart, dissociates. And so what happens is you have your oxygen and your hydrogens, okay? Actually, your water here, your little water molecules here. And what happens is you see that the negative ends are being attracted to the positive ends, and the positive ends of the water being attracted to the negative ends of the bromine. Okay, so your best answer here is D. Hydrogen atoms create attractive forces. There's no bonds being because nothing's touching here. All right, over here, right? So it's these attractive forces with the bromine ions. On the back side of this, determine the oxidation numbers for the underlines. So we need chlorine here. Now with these, the surefire way, it's a little bit longer way, is to do some math. So I have sodium, which has a rule of +1. Chlorine does not have a rule, so I'm going to keep chlorine there. Oxygen does have a rule of -2, and I have 4 of them. Because there's no charge given, the overall charge has to equal 0. So when I do the math here, Chlorine, this is -8 plus 1 is -7. How do I get chlorine by itself? Well, add 7 to both sides, which means chlorine equals a +7. AS does not have a set rule for it, so when I add that to oxygen, which has a -2, and there are 4 of them, now instead of setting it equal to 0, this right here indicates that this overall charge is a -3. Okay, so when I do this, AS plus -7 to get this by itself, add 7 to this side, and I should get, sorry, -8, not 7. I should get a +5. Okay, oxidation and reduction. So identify what is oxidized and being reduced. So this negative means that we start off with a -1 here. Chlorine doesn't have a charge and it's diatomic, so it's going to start as a 0. Bromine is diatomic, no set charge, and the chlorine, I see this negative here, so that means there's a -1 right there above chlorine. Okay, so if I look at bromine first, bromine's going from negative to positive, which means it's becoming more positive. That means that bromine is what's being oxidized. Chlorine 0 to -1 becoming more negative. That means it's being reduced. So chlorine should go there. When I look at this equation for oxidation reduction, well, 0 because it's by itself, 0 because it's by itself. Oxygen always has a -2. Hydrogen has a +1. Well, for this is -2, and this overall charge has to be 0. This has to be a +2. Okay, so when I look at hydrogen, its charge has changed, and so has copper. Oxygen has not changed anything, so oxygen should not fall down in our equation. So what's being oxidized, what's becoming more positive? Well, that's hydrogen. Hydrogen starts out at a 0 charge, and that produces hydrogen +1 by kicking off 1 electron. Copper starts at a +2, and 2 electrons have been added to it to get copper at a 0 charge, because the electrons have negative charges to it. Number 35, this looks like a dilution problem because I'm given 3 variables. So how many liters of a 15 molar, looks like my V1, are needed to make this solution over here? Once again, this is milliliters, and I need to change it to liters. So it should be 0.225. And there's my molarity. I have 3 sig figs, so my answer should be in 2 sig figs. So when I do this, it comes out to be 0.0015 liters as my answer. Okay, these zeros do not count as sig figs. They're not sandwiched. They're just placeholders. So 1.5, there's my sig figs. Okay, 36. If you have 43 milliliters, that's not good. I need liters. So it should be 0.043 liters of a 3 molar solution, and you want to dilute it to a 1 molar solution. How much volume do I need to add to it? Okay, so once again, this doesn't indicate, so I'm going to leave it in liters as my answer. When I multiply this out and really divide it by 1, divide both sides by 1, I should get 0.129 liters, because 3 sig figs, 3 sig figs, 3 sig figs, I should have 3 sig figs in my answer. Okay, that is in the quiz. I hope that helps.